All right, we are now going to begin the third video in the mechanical power transmission notes. This should be the last video for this unit. Now, uh, we talked earlier about pitch diameter or diameter pitch and how the VEX system has the 24 diameter pitch system. And since the gears are proportional, or since the teeth of the gears are proportional to the diameter, we can use the tooth count in the math. Now, here's what I mean by this. If we have an 84 tooth gear, its diameter is 3.5 inches. And for a 60 tooth gear, its diameter is 2.5 inches. Now, if I were to set this up where I had the 60 tooth as my input and the 84 tooth as my output, when I would go to calculate the mechanical advantage of this system, I could do 3.5 inches divided by 2.5 inches, and that would give me a mechanical advantage of 1.4. Notice, however, if I did 84 divided by 60, I get 1.4 also. So what this means is that you don't have to go around measuring the diameters of all of the gears. You just simply have to use the teeth. If you know the number of teeth on the gears, then you can go ahead and calculate that. So just reiterating here, the gear reduction formula, or the mechanical advantage for gears, will be the output teeth, number of output teeth, divided by the number of input gear teeth. So let's look at some math here then. Here's what I have. I have a 60 tooth gear meshed with a 12 tooth gear. The 12 tooth gear is my input. The 60 tooth gear is my output. The free speed is 100 RPMs, and I'm going to use 1.67 Newton meters for the stall torque. And what I want to know is what is the output speed and the output stall torque. So, getting us started then, the mechanical advantage would equal 60 over 12, which is 5. So the mechanical advantage of this gear system is 5. So when I go to calculate torque, well, the output torque equals the input torque times the mechanical advantage. So the output torque would equal 1.67 Newton meters times 5. So I see an increase in torque. Torque is increased. Well, that means we have to sacrifice speed. So to get the output angular speed, that's going to equal the input angular speed divided by mechanical advantage. So it's a little different here. So for us, the free speed of the 393 motors is 100 RPMs. So that divided by 5. So we see that the output speed is 20 RPM. So what we see in this configuration of a small gear going to a large gear is that we increase the torque, but we have to sacrifice speed to do it. All right, let's reverse that then. This time, the 60 tooth is the input, the 12 tooth is the output. Once again, our input is going to be 100 RPMs. Our output, I'm going to go back to 1.67 Newton meters. All right, so this time, mechanical advantage is 12 over 60. That's going to be 0.2. So the output torque equals the input torque times mechanical advantage. So we see that the output torque now is 0.334 Newton meters. For rotational speed, we get 100 RPMs divided by our 0.2, which gives us 500 RPM. So when we have a large gear driving a small gear, we see a loss in torque, but an increase in rotational speed. Now this picture right here is a nice little graphic, and it just lists all the different possible combinations of our 4 gears. We got 12 tooth, 36 tooth, 60 tooth, and 84 tooth gears, and this just goes through and works through all different combinations. So feel free to use this when you're working out problems, just to kind of get a quick little idea. And this gives us all the mechanical advantages. Okay, so our next topic then is the idler gear. And sometimes you can't put a motor very close to a wheel or to an application. So what we need to do is we need to have some space between the motor and where we're applying it. That's where idler gears come in. An idler gear is used, basically, it helps us add distance between the driving and the driven gear, or the input and the output. And also notice that it reverses direction. If I only had 2 gears in a system, notice that they will always spin in opposite directions of each other. But if I need the input gear and the output gear to turn in the same direction, notice how the idler gear allows that to happen. So idler gears have 2 purposes. They add length to a gearbox, and they also change direction. But how does that affect the mechanical advantage? Well, let's find out. Remember that mechanical advantage is output teeth divided by input teeth. So here, again, this is the input side, this is the output side. Output over input, so I would have 36 divided by 12 for these first 2, times 60 over 36 for the second 2. Notice that the 36's will then cancel, and we're left with 60 over 12, which equals 5. So that is an unfortunate thing. The idler gear, or maybe it's fortunate, the idler gear does not influence the mechanical advantage. It only adds length and changes the direction of the rotation. It does not affect the mechanical advantage between the input gear and the output gear. As a proof of that, let's take a look at this really ridiculously long gear train. Now let's figure out the mechanical advantage. Okay, so we have the first one here. So that's going to be 36 over 12 times. Okay, this next one is 36 over 36 times. And I'm just doing output over input. That's all I'm doing. Now, notice we have a lot of cancellations going on here. So we're still stuck with a 60 to 12 tooth gear, which is still a mechanical advantage of 5. So that is how we calculate mechanical advantage when we have a long line of gears. Okay, so moving on then. What about compound gears? You know, what I've shown you so far is what we call non-compound, where all the gears are in a single line. And the idler gear does nothing to affect the mechanical advantage. And if you think about it, that's kind of a problem, because that means that the greatest mechanical advantage we can get is between a 12-tooth and an 84-tooth gear, which is 7. In some situations, we need more. In these cases, we can use a compound. So first off, let's take a look at a non-compound. Notice how we have single line gears in a line. Well, in the compound gear, we have a shared axis, and we have 2 gears on one of those axes. So in a compound gear system, there are multiple gears, multiple gear pairs. Each pair has its own gear ratio, and a shared axle connects the pairs to each other. So the resulting compound gear system still has a driving and driven gear, but the gear reductions are much, much greater. So let's figure out the mechanical advantage of this guy. So this is our input side, this is our output. Notice that what we should be doing is increasing torque and decreasing speed. So to figure out this math, again, it's output over input. So here I have a gear pair, so this mechanical advantage will be 60 over 12 times, but this time here is my gear pair, 60 over 12. Hopefully you can see how that math is different. Obviously this equals 5 times 5, which equals 25. The mechanical advantage now is 25. So if I were to have a single 393 motor attached to this, what I would have then would be the output torque equals the input torque times mechanical advantage. So that would be our 1.67 Newton meters. That's for the 393 motor, times 25. So that gives me an output torque of 41.75 Newton meters. Much, much greater. And then we would have our output speed equals the input speed divided by mechanical advantage. So for the 393, that's 100 RPMs divided by 25, which equals 4 RPMs. You'd only get 4 rotations every minute. That concludes video 3, and we will be finishing up the notes in video 4.